Okay, so G5 and G6, the next two sections that we're going to be doing are both kind of the same technique. It's called separation of variables. It is a way to solve differential equations. This method only works when equations are set up the right way. There's classes in college, that are devoted to just differential equations, because most differential equations that show up in like real world situations aren't necessarily always the easiest things to solve, or even do we have ways to solve them. But this is just kind of like an introduction to kind of end off the calculus class of like, here's a type of problem that we can solve. In most cases, in the real world, you would not be able to solve, just a general differential equation. And there's all kinds of different techniques that are used to solve those things. But all these will be able to be separated. We're going to look at 4 examples today and kind of let you guys practice these. From doing these, what I remember is you kind of want to look for certain setups. There's going to be like 4 or 5, that's just a number I'm pulling out of the top of my head, different setups that you're going to see repeated throughout these questions. And you've got to look for that setup and execute on it the correct way. It's one of these deals where people start like mix matching, like, oh, I have this, so it's this one, but they get it completely wrong because they just kind of get into autopilot. So make sure you know what you have, make sure you're doing the correct thing each time. It is just integration, by the way. We aren't doing anything new. But like I said, there's just a handful of patterns that are going to be repeated, and we just want to make sure that we get them right. Okay, so it's called separation of, let's start up at the top. What we're going to be doing is kind of like doing implicit differentiation, but backwards. So recall implicit differentiation. This is where we're trying to find dy dx, but we have an implicit function. So because we're taking with respect to x, anytime we take a derivative that's only involving x, we don't need any chain rule stuff. The derivative of x squared is 2x. Since we're taking with respect to x, however, when we do y squared, that derivative is going to be 2y, and then with the chain rule, multiplied by the derivative of dy dx. And then kind of a minor thing here, but it kind of really brings home the point of what's going on here. When I take the derivative of 9, I get 0. So that little piece there is kind of why we have this whole general solution, particular solution thing that we're going to see. If I take the derivative, I get 9, I get 0. That 9 could be any number, right? And I would get the same equation as when I did the implicit differentiation. So we lose a piece of information when we take a derivative. We no longer know, if I only gave you the differential equation, what I have there, then you wouldn't know that there was a 9 in the original equation. And that's why there are multiple solutions to these differential equations. This is a solution to this differential equation. So it's just really a perspective thing. What's the problem and what's the answer? In implicit differentiation, the black was the problem and the orange was the answer. And then here, in this case, it's the other way around. We would then solve for dy dx, so we would bring the 2x to the other side. And this is just a different form of the same differential equation. Morning. And then our dy dx, if you can kind of handle me canceling out those 2's as well, would be negative x over y. So this is where we're going to start with a dy dx equals, and we're going to work our way back to the original solution, but we're not going to have the 9. We're going to have a variable like c there. That's why if you look at the definition that you copied down at the beginning of class, that c is what I'm calling a parameter variable. It's some variable, but it's just a number that we don't know. It's not something that can change. It's a set number we just don't know. Okay, so let's take a look at a couple examples. The idea here is we're going to translate from the language of derivatives, where we have the dy and dx together, to the language of integrals, where we have the dy and the dx split, and we've got to keep everything algebraically sound. So we're going to do algebra on this. We could think of it as multiplying both sides by dx to get that dx over to the other side. That's not really what we're doing, but it works that way, so we'll think about that. And we'll multiply both sides by y as well. And then that should give us something that we can integrate. So multiplying both sides by y puts the y on the left and takes it away from the right. Like I said, we're going to write this in the language of integrals. So we're going to bring the dx over to the other side. If I just gave you that on day one of class and said cross multiply, that's probably what you would come up with, right? You might not have known what the dy and the dx were, but maybe it's just, back to day one, it looks like two separate variables, a d and a y. Maybe you would have written dy squared, which would have been wrong, but in essence, that's kind of what we're doing. Don't leave it like that, though, because we're in the language of integrals. We want to integrate both sides. Now, these are indefinite integrals. So when we take an indefinite integral, we should have a plus c. But because it's an equation, we only need that plus c on one side. If I have a thing plus any number equal to a thing plus any other number, I can just say that my thing equals the other thing plus a number. That's a little bit wordy. But if this ended up being a plus 5 and this ended up being a plus 7, I could subtract the 5 from both sides and make that a plus 2. So we usually only put our plus c on the right-hand side of these equations. You don't need the two separate variables. So here's our first pattern. When your left-hand side is just a y, you're going to end up with y squared over 2. Like I said, we're not going to put the plus c on that side. And then that's going to equal x cubed over 3 plus c. And then I just need to solve for y, which is going to give me, first, by multiplying by 2, y squared equals 2x cubed over 3. Now, you have to be thinking when we're doing these. You've got to be thinking about what's happening to your c. This c could be any number in the world, and I'm going to multiply it by 2. Can that c still be any other number in the world? We're going to leave it alone and write plus c. Okay. Because what that says is my y squared is this thing plus any other number in the world. And, in both cases, you're just putting that 2 in there just complicates things. So this doesn't look algebraically correct. I've seen some people actually kind of like subscript these. So they'll call this C1 and then they'll call this C2, but that's not necessary. So I don't like to do that. Okay, I got to get the y by myself. So what do I have to do to both sides? Square root it. Yep. So I'll square root both sides. I'll do a different color. And I end up with y equals plus or minus the square root of 2/3 x cubed plus c. No real good reason why I moved the x out of the numerator, but maybe it was just my dipping down square root bar is part of the reason why I did that, but those are equivalent. So that's one of our patterns. One of our patterns is you'll integrate y on the other side. You're going to get a square root. Don't forget to put the plus or minus there. Later on when we do particular solutions, we're going to have to choose. A general solution represents all the different curves. So if you think back to the first day where I was doing slope fields and I had a slider and the curve would move around the slope field, that's what this equation represents. Change that c and that moves your curve around the slope field. This isn't a function because it actually represents a family of curves. When we solve for particular solutions later on, we do need to have a function. The reason this is a function is you could get different results for the same x. You could get the positive version or you could get the negative version. So that'll just a little bit of a preview ahead. When we're doing particular solutions, we'll actually have to pick. Is it the positive version? Is it the negative version? Okay. But that is the general solution. That's what I was doing to set up those slope fields. So I would solve the equation, put this in and then let Desmos change C, and that's what would move the curve all around the slope field. All right. One down, let's take a look at another one. All right. So same deal. It feels like cross multiplying. We don't have a denominator, so we're going to end up with, actually, no, it doesn't feel like cross multiplying. The last one did. This one doesn't. This one I have to divide both sides by y squared. Right? That's the only way to cancel that y squared. We want to get our y's to the left and our x's to the right. So that's going to give me y squared dy. And again, now bringing that x to be in the language of integrals, I get sine x dx. That's what separation of variables is. I've got all my y's on one side, I've got all my x's on the other side, which means I can put an integral symbol in. That's not correct. That should be dy over y squared. There we go. Any sense? Yes. No. This is the master fraction bar. Yep. I took the dy dx and I divided it by y squared. Yep. Good question, though. But yeah, no, that is what I did. Dy dx isn't a fraction bar, it's a symbol. So it's a thing over a thing. Yeah. Symbol that happens to look like a fraction. So what's an antiderivative for 1 over y squared? Negative 1 over y, correct. And an antiderivative for sine x is cosine, is negative cosine x. Good, good. And then we'll put our plus c on the right-hand side. All right. So whenever we're in this situation, again, like I said, a different pattern. We had y squared over on the other side. Here we have y in a denominator. We are going to reciprocate both sides, which means find their reciprocal. We're just going to flip the left-hand side and flip the right-hand side. Now, be careful with this. That c has to come along. I've got to take, I'm like I said, I'm reciprocating. So my right-hand side needs to be a fraction, and that c has to come into the denominator. I can't just reciprocate cosine x and then put plus c over at the end. That's not going to be algebraically equivalent. So I end up with negative y equals 1 over negative cosine x plus c. Cool. And then I can multiply both sides by negative 1 to get y equals. Now I could just put a negative out in front of my fraction, and I'd be fine if this was an FRQ. But I'm going to multiply that negative inside of my denominator, which is going to give me positive cosine x. I've got to distribute it to the c, but c could be any number in the world. Does multiplying that by negative 1 change the situation? No. So I'm going to write y equals 1 over cosine x plus c. If you put minus c on an FRQ, who cares? It doesn't matter. You're still good. You've given a correct family of functions. If we were solving for that c, your c value would be different than mine, but that's because they get plugged into different functions. But that's what a multiple choice answer would look like. Okay. So when you're doing something outside of multiplying or dividing the c, you need to treat the c like a variable. I wasn't allowed to just reciprocate cosine and then leave the plus c alone. That doesn't work. It's things like multiplying, dividing. I don't think we see it much, but even adding or subtracting. Like if I had c plus 2, I could just make that c. Because it could be any number in the world. All right. Questions on that one? All right. Next pattern. Oh. Yeah. What's that? Y equals x. What do you mean y equals x? What? What do I have to do to both sides? Divide by y. So I end up with dy over y equals x dx in blue. So we'll integrate ln absolute value of y. Yep. x squared over 2. Okay. All right. So third pattern, common one to see. I'll say it for like the gazillionth time. The only time you get an ln is when you have something to the first power. If this is any other power down here, it's power rule. You never end up writing like ln of y squared. That's never correct, but sometimes it happens. How do I get rid of that ln y? E to the, you exponentiate it. I always like this because I get to use the verb form of our things like reciprocal and exponent. You exponentiate both sides. So I'm going to take e and raise it to the left, take e and raise it to the right. And that this was the one where it gets interesting. So we have the absolute value of y equals e to the x squared over 2 plus c. All right. So now, what's kind of happening here is I've got some exponent rules I can play with. If you have e to something plus something, normally we've put this together because we had two e's being multiplied by each other. I'm going to show more steps here to show the algebra than you actually need to show in real life. If you have e to, or anything raised to a power that's a sum, you really just have two copies of those things being multiplied. So we have e to the x squared over 2 times e to the c. But I'm going to switch the order of those two things. Because that e to the c could be any number in the world. So e to the c could not be any number in the world, but any positive number in the world, right? Yeah. So e to the c could be any positive number in the world. And that actually is going to, that fact is going to kind of help us get rid of those absolute value bars. So I know that to find my y value, the positive version of my y value, I take any number in the world and multiply it by this function, e to the x squared over 2. In this sentence, I don't know whether my y is positive or negative, but I can tell you that y equals, usually we use a capital C. I'm going to replace e to the c. Actually, no, I'm going to do two steps here, but I'll mark which steps I won't show when I'm done here. So my y equals plus or minus e to the c times e to the x squared over 2. I don't know if y is positive or negative, but I know it has this absolute value. So the actual y is either the positive version of my function or the negative version of my function. Does that make sense? But now I have plus or minus any positive number in the world. Can't this thing here just be any number in the world? It can now that it's got that plus and minus. That's how you get rid of an absolute value bar. You put a plus or minus in front of your thing. So I'm going to replace, and just kind of standard what people do, I'm going to replace that with a capital C. There's nothing that says you have to do that. Plus or minus any positive number in the world. Why not just say any number in the world? Capitals usually gets there just by kind of convention. Okay, so what would I write to show this work? I think I would skip the whole second line. Actually, I would skip both of these lines. So when you see a plus c at the end, because of the algebra that I just crossed out in green, you could put a capital C in front of your exponential. Okay. Why? Because it's algebraically correct to do that. You also get to drop the absolute value bars as part of that process. Because that thing was a plus or minus, you would have to put a plus or minus in front of it, but putting a plus or minus in front of any number in the world still gives you any number in the world. See if we should save one for tomorrow. Yeah. Yeah, we'll do that last example tomorrow and let you guys get started on these.